Now we will discuss different fuel cycle options. So far, we have discussed all steps in an open or once-through fuel cycle, from mining till final geological disposal. It is called an open fuel cycle, as there is no link back to the fuel cycle. But the cycle can be closed when the spent nuclear fuel is not regarded as waste, but as a valuable energy source. If we look back at the composition of spent nuclear fuel, it shows that more than 96% of it consists of uranium and plutonium. Comparing the isotopic composition of uranium before and after irradiation, we see that in this example, 3/4 of the fissile uranium-235 is consumed. Isotopic composition of plutonium shows that the majority of it is fissile, plutonium-239 and plutonium-241. This means that spent nuclear fuel still contains valuable fissile material for energy production. The aim of reprocessing the spent nuclear fuel is to recover uranium and plutonium so that it can be recycled as fresh fuel. Doing so, the fuel cycle is closed. The new fuel will be a mixed oxide fuel, a MOX fuel, as it is a mixture of uranium dioxide and plutonium dioxide. The main fissile nuclide in MOX is plutonium-239, so that depleted uranium can be used for the uranium dioxide part of it. MOX fuel is being used in commercial light water reactors, for example, in France, Belgium, and Japan. Reprocessing includes the following major steps. First, a mechanical process separates most of the spent nuclear fuel from the assemblies and claddings. Then the spent nuclear fuel is dissolved in nitric acid with careful treatment of the off gases and residues. In the following step, a solvent extraction process separates uranium and plutonium from the fission products and minor actinides. And the uranium and plutonium nitrates are then converted into uranium and plutonium dioxides. And finally, the waste, mostly high-level waste, containing the fission products and minor actinides, has to be handled appropriately. The most used extraction process, called PUREX, which stands for plutonium uranium extraction, is based on liquid-liquid extraction principles, where a substance is extracted from one liquid into another immiscible liquid phase. In this case, uranium and plutonium are extracted from the aqueous nitric acid phase to an organic phase, kerosene, containing TBP, tributyl phosphate, as the extracting molecule. On an industrial scale, this process is performed by a series of centrifugal contactors, one after the other, repeating the process, so that at the end, high extraction efficiencies are reached. Out of the organic phase, plutonium and uranium can be separately back extracted to the aqueous phase. There too, plutonium-4 is reduced to plutonium-3 by the addition of uranium-4 nitrate, or iron 2+. Plutonium-3 is then back extracted to the aqueous phase. In order to back extract uranium out of the organic phase, the aqueous phase is changed to diluted nitric acid. Uranium is now more stable in the aqueous phase and transfers back to it. Plant scale performances of the PUREX process reach recoveries of uranium and plutonium of 99.9%. Reprocessing creates some high-level waste, like the aqueous fraction containing fission products and minor actinides, which needs to be disposed of in an appropriate way. There too, the high-level waste is first concentrated and calcined. Then it is mixed with borosilicate glass frit and heated at 1100 degrees Celsius. And this liquid glass mixture is poured into stainless steel canisters, and after cooling down, letting the glass solidify, the canister is welded shut and can be transported to the interim storage. Also, more advanced fuel cycle options are being studied. In partitioning and transmutation, PNT, the aim is to reduce the long-term radiotoxicity of the high-level waste from spent nuclear fuel, compared to the same amount of natural uranium, from more than 100,000 years to 1,000 years, or even less. Scenario studies show that this can be achieved by not only recycling uranium and plutonium, but also the other minor actinides. You might remember from the previous lecture that the actinides are the main contributors to the long-term radiotoxicity of the final disposal site. There are two distinctive parts in PNT. The partitioning regards the separation of the minor actinides after the Purex process, and the transmutation regards the burning of the long-lived plutonium and minor actinides into shorter-lived nuclides. For an efficient transmutation, a thermal neutron spectrum is not well suited. You need a fast neutron spectrum. For a successful PNT scenario, we need separation efficiencies of more than 99.9% in combination with fast reactors for the multiple recycling of plutonium and minor actinides with transmutation efficiencies of 10–20%. The choice for an open or closed fuel cycle differs by country. Countries like Sweden, Finland, Germany, USA, Canada have chosen for the open fuel cycle. Other countries like France, UK, Japan, China, Russia for a closed fuel cycle. Countries like Argentina, Brazil, and South Korea, they did not decide yet. Research in more advanced PNT options are ongoing in many countries. An excellent source of actual information for the nuclear activities of many countries is the document Country Nuclear Power Profiles by the International Atomic Energy Agency. That's it. Now you have a flavor of what is the nuclear fuel cycle all about.